Now let us go to an important section in the trigonometry where we are going to study various new formulae. To begin with, we have something called as compound angle formulae. So what that means is, like so far in the previous cases, what identities we have seen, they contain only one angle, which we typically use to denote by either theta or x. But what if we have a sum or a difference of two different angles, and we have to calculate the trigonometric ratios of that sum or difference of angles? So that is where we have the compound angle formula. Now out of these, the most fundamental result is that for cos of a minus b, where a and b are any two angles. So the question is, how do we calculate the cos of a minus b, right? So let us derive the formula for cos of a minus b, and later on all the further subsequent results will be derived from this single formula only. So now the motivation for deriving this particular result is as follows. So let us first consider a standard circle, right? Now let's take some point, say point P, which is making an angle of say A with positive direction of x-axis, right? So the radius vector OP makes angle of measure A. So that means the coordinates of P are nothing but cos A and sin A. That is, we know that cos is the x component and sin is the y component, and we are assuming the radius as 1 because it's a unit circle. Now let's consider another point Q on the circle, okay, which makes an angle of B with the positive x-axis once again. So that means the coordinates of Q are nothing but cos B and sin B respectively. That means if you look at the angle between the radius vectors of P and Q, so the green colored angle, right, so that angle is nothing but A minus B. Right. Now to calculate the cos of A minus B, we follow an important trick. That is, let us first consider, or let us first look at the distance PQ, the straight distance PQ, as if we join points P and Q. So the segment PQ will have the length as shown in yellow color here, right? What do we do is, we rotate these two arms, that is OP and OQ, keeping the angle between them, which is A minus B, the same. We just rotate them so that the point Q touches x-axis, that is point Q is now present on the x-axis. So that means, how does it look like? We are going to transform the figure like this. Now OQ was present here making an angle B, so now the OQ will be present here and OP will be present here because P and Q both would have moved down, isn't it? Now the angle between them is nothing but A minus B. Now radius being 1, coordinates of Q in the new position become 1 and 0, and now the angle made by the radius vector OP is A minus B, so therefore coordinates of P now become cos of that angle and sine of that angle respectively. These are the new coordinates of P and Q. But if you observe, the length of the segment joining P and Q will be essentially same as the length which was earlier, because that length wouldn't have changed. So therefore what we do is, if we want, we can denote the two new points as P dash and Q dash to avoid the confusion. So therefore clearly PQ is same as P dash Q dash. So this is where we use the distance formula to calculate the lengths and equate them, which will give us the expression for cos of A minus B. So before we move to the next slide, let us make sure that we remember the terms. That is, P dash Q dash is nothing but the distance between the point cos A minus B, comma sin A minus B and the point 1, 0. whereas PQ is the distance between the point cos A comma sin A and cos B comma sin B, right? So let us go to the next page and do the quick derivation. Now here let's write as P dash Q dash is equal to PQ. Therefore we can write P dash Q dash square is equal to PQ square, because ultimately in the distance formula we will have square root on both sides, which we can eliminate by squaring both sides in advance. So therefore here we have cos of A minus B minus 1 the whole square plus sin of A minus B minus 0 the whole square is equal to PQ is nothing but cos A minus cos B the whole square plus sin A minus sin B the whole square. So therefore on left side on expanding we get cos square A minus B minus 2 cos A minus B plus 1 plus sin square A minus B is equal to, on right side we get cos square A minus 2 cos A cos B plus cos square B plus sin square A minus 2 sin A sin B plus sin square B. Now let us see what has happened. If we look at the terms cos square A minus B plus sin square A minus B, that gives us 1. That one and another one on left side gives us 2 as a net constant term on the left side. On the right side we have the terms cos square A plus sin square A giving us 1, and similarly cos square B plus sin square B also giving us 1. So 1 plus 1 becomes 2. So effectively all these terms can be cancelled as shown here. Now in the remaining terms you see that minus 2 also can be cancelled on both sides. So therefore finally we arrive at the result cos of A minus B is equal to cos A into cos B. You see both the terms on the right side now will be positive after cancelling minus 2. So we will be left with cos A cos B plus sin A into sin B. So therefore this is the fundamental formula which we call as compound angle result, and this will be used in proving the remaining results as shown here. So let us go to the next variation, that is, suppose instead of A minus B, what if we had A plus B? So how to find out that particular expression? So if we have cos of A plus B, then we can easily write this in terms of the subtraction as cos of A minus minus of B. So you see clearly now we have written the right side as cos of subtraction of two angles, and using the result that we just proved for cos of A minus B, we have cos A cos minus B plus sin A sin minus B. And previously we had seen the negative angle result. We know that cos of the negative angle is same as cos of the positive angle, so that gives us cos A cos B. But whereas sin of negative angle results in negative of sin, so therefore ultimately it becomes minus, and we have sin A sin B. So therefore we get cos of A plus B is equal to cos A cos B minus sin A sin B. And it's very easy to remember, because like if the sign on the left side is minus, then sign on the right side will be plus. So in this way you can remember both of the formulae together. What is important to note is the terms on the right side are in pairs of the similar ratios, that is both the cos and both the sines. Now let us see the similar results for sine also. Now here we once again use the fundamental identity that we are aware of, that is sine of any angle can be written as cos of pi by 2, that is 90 degrees, minus the given angle. Now here we do a little adjustment, that is here we write this as cos of pi by 2 minus a minus b. Now let's see what happens. Now here once again we have cos of subtraction of two angles, so that we can write as cos of pi by 2 minus a cos b plus sine of pi by 2 minus a into sine b. But we know that cos of pi by 2 minus any angle is sine of that angle. So therefore we have sine a into cos b plus sine of pi by 2 minus any angle is cos of that angle, that is cos a into sine b. So that proves the result for sine of a plus b. So here if you observe, in case of cos it was cos cos and sine sine as the two terms, but here in case of expansion of sine we have sine cos and cos sine type of combination. And with sine of a plus b we can also derive sine of a minus b with the similar procedure as we did for cos. Here a minus b can be written as a plus minus b. So we write it as if it's a sum of two quantities. So that is equal to, and we have already proven the result for sine of sum of two angles. So that is sine of first angle into cos of the second angle plus cos of first angle into sine of second angle. So that means we have sine a cos of minus b is same as cos b, negative angle result, whereas this sine minus b will result in minus sine b, making thereby the second term as negative ultimately, and we get cos a sine b. So therefore sine of a minus b turns out to be sine a cos b minus cos a sine b. So which is again easy to remember. If the term were plus, the sign were plus in the left side, so the right side also will have the plus sign in the middle. So here the plus and minus are same signs on both the sides in case of sine. Let's go ahead and derive the formulae for tan also on the basis of sine and cos. So here tan can be written as sine upon cos, so therefore it's tan a plus b is equal to sine of a plus b upon cos of a plus b. Now our intention is to express the right hand side in terms of the tans of the individual angles, right? So in order to do that, what do is we expand both the numerators and denominators using the known formulae. So sine of a plus b is sine a cos b plus cos a sine b divided by cos of a plus b is cos a cos b minus sine a sine b. Now we apply another intelligent trick, that is, look at this particular term cos a cos b. We divide both numerator and denominator by cos a cos b. So what happens is when we divide the first term in the numerator, which is sine a cos b, by cos a cos b, the cos b will get cancelled and we will be left with sine a upon cos a, which is nothing but tan a. So in the numerator we get tan a as the first term. Now in the second term, when we divide cos a sine b with cos a cos b, we'll see that it's cos a that gets cancelled and what remains is sine b upon cos b, which is nothing but tan b. So therefore we get tan b as the second term in the numerator. In the denominator, first term becomes 1 after dividing by cos a cos b, and minus in the second term you have sine a upon cos a as tan a, and sin B upon cos B as tan B. So here interestingly we have a product of the two tan terms. So this is what the formula of tan of A plus B. So interesting that we have derived that result in terms of the tan of the individual angles A and B. Similar to tan of A plus B, we can have tan of A minus B also, and that will turn out to be mere change of signs in the previous result. So that comes to tan of A minus tan of B upon 1 plus tan of A into tan of B, and this also can be proved with exactly same procedure.